So good morning to all of you MSc first year physics student. So today again welcome to lecture series in quantum mechanics, and we want to continue our third chapter is the angular momentum, and in this lecture we want to see the basic idea of the spin angular momentum. In the yesterday lecture and last few lectures we have already seen the idea about or the concept of understanding the orbital angular momentum and total angular momentum. And today in this lecture, this point we want to see here, so that is the spin angular momentum. And before starting this point, we want to see the experimental evidence of the spin angular momentum. And this experimental evidence, which is shown by the very good experiment which is taken by, and this experiment name is the Stern-Gerlach experiment, which is the Stern-Gerlach experiment. Stern-Gerlach experiment. Okay, and what is this Stern-Gerlach experiment? So that is the beam of the silver atoms. Okay, or when a beam of silver atom which is passes through a non-uniform or inhomogeneous magnetic field, so this beam line which is split into the two components which is corresponding to the spin up and spin down. What is this Stern-Gerlach experiment? So for example, this is the magnet, okay, and this magnet which is having the inhomogeneous or which is considered as the non-uniform magnetic field, okay, and if the beam of the silver atom which is passing through the non-uniform magnetic field, so what happens here? So for example, here the screen is present, okay, and this beam which is what is beam? So that is the beam of the silver atoms, okay, beam of silver atoms, and this beam of silver atom which is passing through this magnet, and this magnet having the non-uniform magnetic field. So this beam which is split into the two components, and this two component which is nothing but the spin up and spin down component, okay. So that is the spin up and spin down component. So this is the screen, okay. This is the spin up component, and this is considered as the spin down component, okay, spin down component. So see here, and this is the magnet. So that is when a beam of the silver atoms which is passing through the non-uniform or inhomogeneous magnetic field, so this beam or component which is split into the two components, that is the spin half, or which is considered as the spin up and spin down, or which is generally say that spin half and spin minus half, okay. So that is the spin down. Again next, that is the graphical representation of the spin half. Next point we want to see that the graphical representation of spin half. Graphical representation of the spin half. What is this graphical representation? So that means if we consider the tip of the S bar which is lies on a circle, so that is we have to know that the spin value which is considered as the spin half, and if we consider that the spin up and spin down, so that is the spin up value is half and spin down value is minus half. This is only consideration. We have to not analyze that the spin half and spin half. This is only the theory, okay. So that the tip of the S bar which is lies on the circle of the radius, so S bar is equal to under root of 3 h cross by 2. So for example, how it is possible? That is, if we consider, so that S value is equal to what? Half. Okay. So if we consider the spin value, so that is the S. What is the value of S or formula? So that is the S is equal to H cross into under root of S into S plus 1. Okay. So if we this calculate, so that S is equal to H cross into S value which is considered as a half into this S plus 1, so that is the half plus 1. Okay. And if we doing multiplication of this, so that S is equal to H cross into under root of, okay, this half into this half plus 1, which is nothing but the 3 by 2. Okay. And this final calculation is nothing but the H cross into under root of 3 by 4, and this value is nothing but the under root of 3 divided by 2 H cross. Okay. So this is the graphical representation value of the spin half, and this is the magnitude of this spin half. And if we see the graphical representation of this, so this is considered as this, if the beam of the silver atom which is passing through this Stern-Gerlach experiment in the non-homogeneous or inhomogeneous or non-uniform magnetic field. So if we consider this spin component which is travel along the z axis, so this is considered as the Sz. Okay. And the spin component which is nothing but the spin half and spin half, actually this spin component which is integral multiple of 1 by 2. Okay. And if we consider, so this is the value of the plus spin half, and this is the value of the minus spin half, and this is nothing but the H cross by 2 and minus H cross by 2. For spin half value, which is given as the H cross by 2, and spin down value which is considered as the minus H cross by 2, and this is the component of S bar. This is the spin component of the S bar which is shown is here. Okay. So that is nothing but the S bar, and this is nothing but the EMS value, so that is EMS is equal to H cross by 2 and EMS is equal to H cross by 2. Okay. Minus H cross by 2. So actually what is, so that consider here, so for example value S comma EMS, so this value is nothing but the for the spin half, so that S is equal to half, and EMS is value is nothing but the plus or minus 1 by 2. Okay. So this is the graphical representation of the Stern-Gerlach experiment. And if we see this Stern-Gerlach experiment, so that beam of silver atom which is passed through inhomogeneous or non-uniform field, so that is the, if we see the argument sec, so that the field were along the z direction, and we would expect classically to see on the screen that the continuous band, that is the symmetric of the undeflected of the z direction. Actually what is mean by that? So if we see the according to the Schrödinger wave theory, however, if the atoms had an orbital angular momentum of the L, and we would accept the beam of split into an odd discrete number. Okay. So what is mean that? So for example, okay, so orbital angular momentum, okay, and which is denoted by the L, which is denoted by the small l, and the beam of split into an odd discrete number. The beam split into odd, and this number is the discrete number. Okay, discrete number. Or discrete number, and this number, which is nothing but the twice l plus 1. Okay, if we consider this l value for this silver beam atoms, which is considered in the ground state, and if we consider that ground state, so the l value is equal to, okay, and this discrete number is l plus 1. For l is equal to 0, this number is what? 1. So that is the, if silver atom in the ground state, so that is considered as only one spot which is seen or occurred on the screen. Okay, so that is l is equal to 0, only one spot on the screen, Okay, if we consider, for example, l is equal to what? 1. L is equal to 1. Okay, so that is l is equal to 1. So what is this number? So that is the 2 into 1, 2 plus 1. So that is the 3 spot, which is the 3 spot on the screen. 3 spot which is on the screen. Okay, and so on. L is equal to 2, so that is nothing but the 5 spot. L is equal to 3, which is nothing but the 7 spot. So that type of, so that is the, what is the pattern of this Stern-Gerlach experiment, and that beam of passing through this non-homogeneous field. So what happens? So that beam which is split into this spin pattern, that is the spin up and spin down. Okay, suppose if we consider the classical theory of electromagnetism and orbital angular dipole moment. Okay, suppose the classical theory of electromagnetism. Okay, so by the classical theory of electromagnetism or electrodynamics. Okay, classical theory of electrodynamics. So if we consider the orbital angular momentum or orbital magnetic dipole moment, which is generated by the orbital motion, and this is which is considered as the orbital magnetic dipole moment. Orbital magnetic dipole moment, and this orbital magnetic dipole moment, which is nothing but, so that mu l, which is nothing but the q divided by twice mc into l bar, twice mc into l bar. Okay, so what is mu l? So that is the orbital magnetic dipole moment, and here l bar, which is nothing but the orbital angular momentum. L bar, which is nothing but the orbital angular momentum. Okay, again Cm is nothing but the mass of this particle, and c is the speed of light. Okay, and if we see this charge q is the positive, then mu l and l will be in the same direction. Okay, if that condition, if q is positive. Why q? Because this is the classical theory of electromagnetics, because charge is there, and if q is positive, if q is positive, then mu l, so that is the magnetic orbital momentum and angular momentum which is travels in or will be in the same direction, will be in the same direction, will be in the same direction. Okay, and if this q is minus, okay, so that is the negative charge, so that such as the electron and this charge which is as compared to minus e, so that is the charge on the electron, so the magnetic dipole moment which is considered as the minus mu l minus e l divided by twice mec. Okay, so that is the next condition, so which is if q is negative, then this mu l, which is nothing but the minus q divided by twice m c into l bar, and we have to consider here this q is nothing but the charge on the electron, so this is considered the minus e divided by m e into c. Okay, and here e is the nothing but the charge of the electron, and m e is nothing but the mass of the electron, and if with this orbital angular momentum of minus q charge, that will be opposite in the direction. So that is the orbital angular momentum, orbital angular momentum, orbital angular momentum will be in opposite direction, will be in opposite direction. Okay, so this is the theory of the orbital angular momentum, which is related to the spin component by the Stern-Gerlach experiment. And if we see the figure of the orbital magnetic dipole moment, and when external magnetic field apply, so what happens, so that we want to see here. So that is that condition, that if q is the positive, then mu l and l which is travels in the, or which is will be in the same direction. So that means what? So the, if we consider the spin orientation, okay, so this is along the z axis, this is along the z axis. Okay, so this mu l which is oriented on the z axis, so that is the, this is the your angular momentum vector, so that is the l bar, and if we see this radius, we have to know that, so what the value, so for this mu l value, which is nothing but, so that is the orbital magnetic dipole moment, so which is the q upon twice mc into l bar. Okay, and this figure, which is nothing but the orbital magnetic dipole moment, this is figure A, orbital magnetic dipole moment, orbital magnetic dipole moment of positive charge of plus q, and if we see the precision of this orbital angular momentum or external magnetic field which is applied, so what is the orbital magnetic moment which is precise about it, and that precision which is considered as, if we consider this x, y and z axis taken here, Okay, so for example, this is x-axis, this is y-axis, and this is the z-axis, and this precision which is along the this z component, so this precision which is like as this. Okay, and default direction is the anti-clockwise. Okay, so this is precision of the this orbital angular momentum. Okay, so this is nothing but the L bar, and we have to calculate. Okay, so that when this condition, if we have to apply the external magnetic field. Okay, so if we apply the external magnetic field, so your magnetic or your orbital magnetic dipole moment which is precise about it, LZ. Okay, if external magnetic field is applied, orbital, then orbital magnetic dipole moment precise about it, which is precise around it. Okay, so this is the figure B. Okay, and if we consider the classical analysis of the picture of the electron which is spinning in the spherical charge, so that the spin dipole moment. Okay, so this theory which is considered as the orbital angular momentum or orbital dipole moment. Okay, and if we consider the picture of the electron, the spinning of spherical charge, so the spin magnetic dipole moment, this is considered the part of the orbital magnetic moment, and this is spin magnetic dipole moment, spin magnetic dipole moment. Okay, and this spin magnetic dipole moment, which is nothing but the formula mu s is equal to what is this formula? So this is considered as minus E upon twice MEC minus E upon twice ME into C into S bar. This E is nothing but the charge on electron, ME is the mass of electron, and this is the spin component. And if we consider, or this value which is nothing but the spin magnetic dipole moment, is mu s is nothing but the minus gs divided by twice ME into C, okay, into S bar. Okay, minus gs to E upon twice ME into C into S bar. Okay, and this gs is nothing but the Landé G factor, and this is value which is considered as a plus 2. Okay, so gs is nothing but the Landé factor. And this value, gs value, which is nothing but the experimental value, Landé factor, or which is considered as the gyromagnetic ratio, and this gs value is nothing but experimental value of gs. Experimental value of gs is nothing but the 2. Okay, so if we consider that orbital angular momentum of particle which is characterized by two quantum number, so that is the orbital number, or this is considered as the L, and azimuthal quantum number which is running from minus L plus 1, minus L minus 1, and up to the L. And if we consider the spin value, so that is the S, and this value which is nothing but the ms is equal to minus s2 plus 1. So for example, consider for orbital angular momentum, orbital angular momentum, for orbital angular momentum, and this value is nothing but for L, your ml value is nothing but the minus L plus 1. Okay, again this value which is running for, or which is considered as the L minus 1 and L. Okay, L minus 1 and L. So this is the orbital angular momentum, and this is ml, which is considered as the azimuthal quantum number. Okay, this is considered as the azimuthal quantum number. Okay, and next, which is considered as the spin angular momentum, and this spin angular momentum, so this value is nothing but, okay, so it is denoted by the capital S. Okay, so and this EMS value, that is the azimuthal spin quantum number, which is considered as minus S plus 1, minus S plus 1 up to the S minus 1 and S. Okay, so this is the value of the spin azimuthal quantum number and the total angular momentum. Okay, so for example, this if we consider that S is equal to half, okay, then S is equal to plus or minus half, and then total angular momentum, which is the combination of this L plus S, so capital J is equal to angular L plus S, that is orbital angular momentum and spin angular momentum, and this is considered as the total angular momentum, total angular momentum. Okay, so this is the experimental evidence or basic study of the Stern-Gerlach experiment, and in the new lecture we want to see, okay, or next lecture we want to see the idea about the general spin theory, or what is the basic of the spin theory and what was the formula and Pauli matrices of this spin theory. So this point we will be seeing in the next lecture. So thanking of you.